I've had a couple of questions from students about this, about problems on SmartWork, so I figured I would go ahead and talk about mass fractions and mass percent. So our background from this is looking at molecular weights for different molecules, and also for looking at atomic weights. And so when you look at a molecular formula like lead sulfide, you know that each of these two atoms is going to constitute some of the weight of the molecule. And if you have a heavy atom like lead has an atomic mass of 207.2 grams per mole. Compare that to sulfur, which has an atomic mass of 32.065 grams per mole. So if we think about one atom that has about 200 grams per mole and another that's about 30, we can see that of these two, it's the lead that makes up most of the mass. So, for example, if I have a certain mass of lead, like let's say I get a 100-gram sample of lead sulfide, most of it is going to be lead, and then by mass anyway, and in a much smaller fraction of it will be sulfur, even though they are 1-to-1 in terms of their atomic relationship, right? We have one lead atom and one sulfur, but because the lead one is a lot more heavy, if we're just thinking about the mass fraction or the mass percent, then the mass fraction of this particular scenario would be the mass of the lead divided by the total mass. And the mass fraction of lead in the lead sulfide 100-gram sample is going to be the same mass fraction as it is in the molecular weight. I'll say that. I'll write that down. The mass fraction, and I'll just be general, of an element in a sample is the same as its mass fraction in its molecular formula or molecular weight. And this is also true for percents. But if we're doing math with these numbers, we'll almost always use the fraction. So even though people talk about mass percent a lot, the fraction is what we use when we're doing math. So we have two atomic masses. So the molecular weight for lead sulfide would be the sum of those two masses. And if I've done my math right, I get 239.3 grams per mole for the molecular weight. So when we are going to find the mass fraction, we're going to take the atomic weight of lead, we're going to divide it by the molecular weight of the whole compound, and that's going to be our mass fraction. If you want, you can multiply it by 100% to get the percent. Okay, so if we put those numbers in, 207.2 grams per mole divided by 239.3 grams per mole, then we will get 0.8659, or in other words, 86.59% if you want to go into percents. So if you look at your 100-gram sample, I picked 100 grams because I can divide it up the same way as the percent. And our fraction of lead is 0.8659. That means that in 100 grams of lead sulfide, 86.59, maybe I'll give an extra 0, grams is lead atoms. And 100 minus 86.59 would be 13.41 grams is sulfur atoms. Okay, so try that again, but with a different number. So for your total mass, let's instead use 485.2 grams of lead sulfide. Okay, so go ahead and do that calculation, pause the video, and then we'll look at the answer. All right, hopefully you already figured this out. So if you're doing this calculation, you're going to take 0.8659 times the total mass for 85.2 grams of lead sulfide. And I got 420.1 grams would be lead atoms. And then 0.1341 times 485.2 grams will get me the sulfur grams. The other way we can do this is just take 485.2 minus 420.1 gram. And that's also going to get us this number, which is, there we go, 65.1 grams of sulfur. So let's look at the process of what we just did. In this whole, here I'll leave this part up. In this whole procedure, for step 1, we calculated the atomic weight of, in this particular situation, it was an element. I'm going to call this quantity A. And you can also do it for like an ion, and we'll look at some examples. I guess an ion is probably the most common. I'm not going to say or other because I can't think of any other situations for how you would do that. All right, so that was step 1. We calculated the whole molecular weight. And that I'm going to call B. For step 3, we calculated the fraction and we dividing A by B. And then if you want 100 for percentages, we have 100%. Okay, so when we did that then, and then we were comparing it to real masses, we found that the mass fraction of an element multiplied by the total mass was equal to the mass of that element or component. And I'll put that detail here. And that's what we did right here. This was the mass fraction, this was the total mass, and this was the mass of the lead. Same deal with the mass fraction of the sulfide, the total mass, and the mass of just the sulfur. Okay, let's try this out with a few examples. Okay, I guess I'm not going to call these examples. I'm going to call them practice problems because I'd like you to practice them. So for practice problem 1, our question is, how many pounds of iron are in 397 pounds of iron oxide? If you already know how to do this, then go ahead and do it really fast. I'm going to walk our way through it, and then I'm going to let you try another problem on your own. So we're going to do step 1, where we calculate the mass of the component that we are interested in. So here's where we need to pay attention to the stoichiometry of our compound too. So our mass of iron is going to actually be twice the molecular weight, or excuse me, the atomic weight of the iron, because there's 2 irons in our chemical formula. So we do have to include that, so please do be careful about that. So our quantity A is going to be 111.69 grams per mole. Our quantity B is going to be the whole molecular weight, which you should get 159.69, if I can read my own handwriting here, grams per mole. So please pause the video and make sure you get that. And then for step 3, we're calculating the fraction of A over B. So pause the video and get that number. Now when I did this, I got 0.6994 for that mass fraction. So this is my whole initial step, and now I need to do this mass fraction times the total mass is equal to the mass of that component. So my mass fraction is this number, my total mass is this number, and then I want to know how many pounds of iron I have. Now, I want to pause here and point out the units. The units are pounds, which is different than the units of grams per mole, and it's not a unit that we use a whole lot, but I wanted to illustrate using this to have you notice that you don't actually have to convert the pounds into anything, because you're starting with pounds, you're ending with pounds, and you're multiplying by a number that does not have a unit, which is the fraction. The fraction has the 2 units cancel out. The grams per mole of A and the grams per mole of B just cancel out those units. So this is a unitless number, so we can go ahead and just multiply it, 0.6994, by the total mass, 397 pounds. And when you plug that in, you should get 278 pounds of iron in the 97 pounds of iron oxide. All right, so let's go ahead and try another practice problem. How many kilograms of oxygen would be in 18.84 kilograms of potassium nitrate? All right, pause the video, calculate your A, calculate your B, calculate your A over B fraction, and then set up your mass fraction times your total mass is equal to the answer you actually want. All right, pause the video and then come back in a minute. Okay, the numbers I got were 47.997 grams per mole for oxygen because we have 3 of them. For B, we get 101.102 grams per mole. So that makes our fraction 0.47474 with all the sig figs. And I got 8.944 kilograms of oxygen for my final answer. So if you have any questions on all of that, then just ask me during class. All right, now what about a slightly different version of this same kind of problem? In these, I was asking you about the quantity of one particular element in a whole compound, a whole mass of a compound. What if we change this question slightly? What if we say, how many pounds of calcium nitrate would you need to have 25 pounds of nitrate ion? So we're going, I guess I actually changed it in 2 different ways. I changed it because this is the question. Well, let's back up a second. The question that we've been asking, we've been taking the mass fraction and multiplying it by the total mass, and then we have our unknown, which is the mass of the component. So when I wrote this problem, we've changed things around. Just like before, we can calculate what the mass fraction is, but we're given the mass of the component that we want, and this is now our unknown, our total mass. But this is not a problem, right? The mass fraction is exactly the same calculation that we had before. We actually, oops, I'm going to draw my arrow into the wrong direction here. This is our unknown, but just like we had before, we still have a quantity of something that's given. And we have algebra, so we know we can just solve for the total mass as our unknown. Okay, so I want you to give this a try. And I want you to also notice that the other change that I made, which I actually paused in order to talk about the rest of this, was that I'm not just asking about one element now. Now I'm asking about a whole nitrate unit. But the mass fraction is exactly the same calculation. It's just we're going to calculate the mass of this whole unit in the molecular formula. So we have 2 nitrates. So find that whole mass, and that's what your A is. All right, pause the video, do this calculation, and check back in a minute. All right, so for A, the mass of 2 times nitrate, I got 124.008 grams per mole. For B, the whole molecular weight for the calcium nitrate, I got 164.086 grams per mole. For my fraction, mass fraction, I got 0.755. I had a lot of sig figs here, 750. So now when I solve for the total mass, I'm just taking the mass of the component, 25 pounds, which is given, dividing by that mass fraction, 0.755750, and that gets me a total of 33.1 pounds of calcium nitrate that I need to use. in order for 25 of it to be nitrate. All right, how about one more practice of the same kind? What mass of nickel chloride is needed to supply 85.15 grams of chloride ion to a reaction? All right, pause the video and go through our steps and see what your answer is. All right, hopefully you're ready to unpause. When I calculated the mass of the chloride, I have 3 of them. So that mass came to 106.36 grams per mole. The total molecular weight was 165.05 grams per mole. My fraction gave me 0.64440, and so that meant that my total mass was equal to 85.15 grams divided by 0.64440, which is equal to 132.1 grams of nickel chloride. All right, hopefully this has answered any questions you might have about calculating or doing problems involving mass percent and mass fractions. And if you have additional questions, please let me know.